All right, hello. My name is Stefano. I work with Fabrizio, and I am part of the organizing team for this event. And it falls onto me to try and explain to you how non-locality and contextuality works in 15 minutes. And so, yeah, wish me luck, please. But luckily, I have 5 minutes of questions where I can hopefully top up what I will have said. The term that I will use today is contextual cryptography, by which I mean cryptography which is enabled by a certain property or resource, which is called contextuality, which is something that quantum systems have and classical systems don't have, hopefully. There you go. And so obviously I'll have to start with a brief definition. And contextuality, you could say, is the impossibility or the inability to take certain pictures or screenshots of reality that you obtain from various contexts, quote unquote, measurements or settings of your experiments or of your cryptographic hardware that give you some random outcomes. And you ask the question, can I explain the outcomes that I observe in a purely classical setting? Can I define what's known as a hidden variable, a secret that someone knows that I don't know? To me, they look random, but to someone else, they don't, maybe? Someone else could attack them. The randomness could be something that I perceive, but is not real, is not secure. And contextuality is the inability to do this. So in a sense, it's a no-go. It's a negative result. It's something which cannot be done classically, which can be done quantumly. But the point of this presentation is whenever you have something that you cannot do classically, perhaps you have a resource that you can use for security or computational advantage. And so contextual cryptography is any form of cryptography which is based on this kind of resource, which I will now try to explain. The simplest experiment that people present when talking about non-locality or contextuality is Bell's experiment. And in Bell's experiment, you have two parties, which we can call Alice and Bob, and each of them has one qubit. But these two qubits that they own are in a very special state. They are in an entangled state called the Bell state. And so they share a certain kind of correlation, but it's more than a correlation. It's a choice of different correlations depending on the measurements that the two parties can perform. And in this particular protocol, they choose between one of two measurements each. They flip a coin, and they measure at a different angle on the equator of the Bloch sphere. So each of them measures their qubit independently. And they obtain a bit, either 0 or 1. That's the outcome of their measurement. And individually, the bits are just 2 bits. But if you collate them together, what you get is a table. You get a conditional probability distribution. And this conditional probability distribution tells you that the outcomes have some kind of randomness. They're not exactly a coin flip. There is a little bit of anti-correlation or correlation residual, but they are correlated. They are quite strongly correlated, in fact. And the question becomes, is this some kind of correlation that we can explain classically? Is this something which could have a classical source? We just don't know it, but secretly somebody tampered with our equipment. We think we're running Bell's experiment, but really we're running a simulation on some Raspberry Pi. And the answer is, well, it's a simple calculation that you can do. You can predict at most roughly 58% of that randomness. The rest is true randomness, is genuine physically based randomness, with the caveat that you have to assume that whoever manufactured the devices cannot break the laws of physics so much that they can signal faster than light. But we will make this assumption silently. If that is broken, then we have no hope. So I think that's fair to presume, at least now, and I will write it down, but in gray, so that you know that it's not really something you have to worry about, hopefully. And if you think of that randomness as randomness used in a cryptographic setting, then this is kind of the end of the talk. This is security guaranteed by the laws of physics. Except, well, we don't really know if that's useful. Yeah, great, we have randomness, but can we use it to do something interesting? In this case, it's kind of obvious. You have some bits that are either perfectly correlated or perfectly anti-correlated. You pick one of the two. Let's say Bob. He does a bit flip on his bit locally, and what you get is perfectly correlated bits in all 4 cases, depending on what the choices was, and they can be used to do key distribution. So you can make a perfectly correlated stream of bits that is secured, at least 42% of it, by physics. And then you can do privacy amplification, and you can bring that up to 100, sacrificing, some complexity, some time, some resources. But nonetheless, you can purify it into almost perfect secure stream. The point is, this is a very interesting protocol, honestly. We know how to do quantum key distribution. We know how to do classical key distribution. We do it all the time. It's how the internet works. So we want to find other protocols that are more interesting, and in trying to find other protocols, perhaps we learn something more about how this kind of cryptography works. What are the basic principles that allow us to discover new things? And as the nicest, second simplest example that I can give you, at least one which is non-trivial, I'll consider what's known as Mermin's non-locality experiment, or Mermin's experiment, or Mermin's game, depending on where you look. And this is very similar to the previous one, very similar to Bell's game, but it now has 3 parties. And what they have each is 1 qubit, but now it's a tripartite state. So it's 3 qubits that are in a weird correlated quantum state, which is called a GHZ state. And what they do is something similar to what Alice and Bob did in the previous example. They do one of 2 measures. These measures are even simpler than the previous ones. It's either in the x-axis or in the y-axis. So again, single qubit measures. They pick one at random, flipping a coin each, independently of each other. And something happens. I don't know. You get that table. So there are 3 possible bits that would give you 8 combinations, but only 4 of them are relevant to this game. The other 4 you just throw away, say, okay, this is one of those rounds where I failed, that I discard this round. So you get about 50% of the round's work, and the other 50, you know that you got useless information. But on those 50% of the rounds that you care about, you get this kind of correlated distributions over the 3 bits. And right now, maybe they look like they have a certain pattern to them, but maybe it's not entirely obvious that they could be useful. Until you notice, come on, there you go, that they do have a very interesting property. If you take the 3 outcome bits, they look random individually, but if you XOR them together, then they always give 0 in one of the 4 settings, and they always give 1 in the other 3 settings. So this is a deterministic XOR, and this is something, it's a property which can be used to do a protocol known as secret sharing, where you have to have 2 ingredients. You have to have the fact that the 3 bits XOR to something known, because that is what you use in the unsealing phase of the secret sharing protocol. You need to know that you can unlock the secret, but you also need them to be random, at least to some extent. In this case, they are maximally random. They are uniformly distributed over all of the possible triplets that have a given XOR. It's 25%, 25%, 25%, 25%. So this is a perfect resource for quantum secret sharing. And indeed, this was used to develop a very well-known protocol known as HBB quantum secret sharing, which goes kind of like this. You have 3 parties, they have a GHZ state, they measure it, they get 3 bits. They keep the bits secret. Then one of the parties is the dealer, in this case Alice. She has the secret, and she wants to distribute it to Bob and Charlie, but only in such a way that they can open the secret, they can learn the secret if they both agree, which in this case is defined by them revealing to the world or to each other their secret outcome bits. So they keep them secret in this phase, but Alice takes her outcome bit and XORs it with the secret bit, and then makes a correction depending on which choices the 3 parties made. So no correction for XXX, and just negates the result for the other 3 options. And then she announces this secret bit, and this secret bit is now open. It's known to everybody, but nobody can really learn what the original X value was. It's uniformly distributed to any observer that doesn't know both OB and OC, the outcomes of Bob and Charlie. In the unsealing phase of the protocol, Bob and Charlie both announce publicly or to each other their bits, and they can XOR them to the secret. And because we had this deterministic XOR property, plus the correction that Alice applied, the XOR of the secret and the 2 bits of Bob and Charlie of the encrypted secret and the 2 bits of Bob and Charlie was the original plain text that Alice knew. And so this is a way to put together the deterministic side of things. So this property that you knew, that you could use to make a protocol like this, together with the randomness that guarantees the security. And this is the core idea of contextual cryptography. Now, is this secure? Well, 0% of the randomness in this particular protocol can be known beforehand or to an attacker. That's one of the beautiful things about this particular example. It's not 42% secure, it is 100% secure. There is, if you do it right, there is no chance that anybody, by tampering with your device, tampering with the infrastructure between you and the other parties, tampering with anything, can do to discover the secret. The secret is secure. So as long as you pass the test that is used to determine the security of this particular scheme, then this secret is 100% secure. This is perfect contextual cryptography. And this is device independent, fully device independent, fully theory independent. As long as the attacker doesn't signal faster than the speed of light, they can make the device for you, they can have super quantum capabilities that you don't know exist, and yet they wouldn't be able to break the security of this, which is exactly what we wanted. It is literally security solely guaranteed by the laws of physics, nothing more. In fact, I should say by the laws of relativity. You also need some quantum to make it, so that's part of the story. Now, this is kind of the end of the technical side of the material, and I'm happy to end a bit earlier and take a bit more questions, but I wanted to give you, by voice, a bit of the story beyond what the technical side is, beyond what the idea of contextuality, non-locality, and the role in cryptography is, and what we plan to do about it. So what is the state now, and where do we want to get in 2, 3, 4 years' time? And the idea is we want to make it possible for anybody to go all the way back to the stage where they say, I know that I want that property. I know that I want a game where I have 3 bits that XOR to a fixed value. They XOR to 0, in fact. Because with this, I can make my own protocol. I don't know anything about quantum at all. I don't know anything about making this secure, but I know that this is the game I want. This is my property. And then we are building a stack that goes from that formal property, that specification, which has nothing to do with quantum, and slowly brings it down to, okay, maybe that game cannot be done perfectly, but you can do a game where with a little bit of local post-processing, you can do it. So you get to a table like that, where you don't get that they always XOR to 0, but they always XOR to something fixed, which you can correct with a simple NOT operation. And then you say, okay, how do I make a state that looks like that, which is also secure? In order for it to be secure, I need to add randomness. How much randomness can I add? In what form? And you discover that there is a state in that, well, there is a table in that form. And then you ask, can I realize this with quantum hardware? And so you make a plan of how you do this in abstract quantum terms, with gates, with states, respecting whatever causality requirements you have. And then you boil it down to practical quantum implementations and all the way to hardware planning. And where you're there, all you really need to do is fabricate it. Because we do have early days, let's admit, but nonetheless, advanced enough capabilities in, for example, photonics, chip manufacturing, that if we have a plan for something and we have enough tolerance on the errors, the transmission losses, the decoherence times, and so on, we could, going from the top all the way just above the hardware, we could then think, okay, now we know that we have a good protocol, it is secure, we know how to implement it, we know the specifics of the hardware, we can just go. So that is the plan. We need to be able to put something which is very hard today. It's hard to do because it requires a lot of specialized skill. We need to put it in the hands of people who have the imagination to make protocols for it. Because that's kind of that's the spark that's missing here. We have one community that is excellent at talking about the security of these protocols, but the best they could come up with is something in the form of QKD, quantum secret sharing. It's not fair, there are a few more, but over the years, these have been the big names. And then we have another community that is great at making protocol design, but doesn't know anything about quantum, and probably doesn't have the interest or the appetite to learn so much that they could get great at device-independent cryptography. So by putting them together, by creating the glue that goes from the protocol design all the way down to the manufacturing side and takes away the burden of having to think about things that honestly a computer can do with enough technological advancement, we think we can really make this possible over the next few years. That is the time I have. There's a few minutes for questions, but thank you for your time. And
so what is the deliverables that you're going for? Are you trying to use this like prove these gates that are already like the experiments, or for like another mathematical primitives, or you're trying to use, for example, the softwares that are available already for like quantum computing, like from this, like Circ, ABM, or are you trying to use the softwares to model these experiments? Like I'm trying to understand like what's the deliverables here.
So there are neither. In fact, we are building a completely new stack. We cannot use. There is almost nothing in the area where we want to build. We do know that there is a nice categorical model based on shift theory specifically, so topological or categorical as you prefer, which can be used to describe this kind of contextual data. And so there are tools that come from the interface between shift theory on the topological side and linear programming on the more geometrical side that can be used to do computations such as how much of this can I simulate classically. So the computation of the security, the exploration of the landscape, it's a very big polytope, but it's one that you can formulate in such a way that you can computationally answer a lot of questions. And what we want to do is, we already have the framework that allows us to answer many of the questions, but there are things that we need to still develop properly, and we need to expand the framework anyway. One of the big things is you don't just have to answer questions on a given protocol, you have to find protocols. So we want to go from you telling us, I have a game, I have a protocol that I like that involves 3 bits that have a constant XOR, and we have to be able to say, okay, then you have a post-processing layer that you have to explore. You have a polytope layer that gives you the tables, and then you have the quantum realizable part, which is not a polytope, is very hard to explore properly, and we have to glue all of this together computationally in order to give an answer to this is a potential implementation of something close enough to what you wanted.
Gotcha. So you're doing the simulations, like the viability of things. Very cool. Do you guys, just one more question, did you look at the software already available? Like there's a lot of, they're doing this for many years, right? Like you can do pretty much any experiment, teletransportation, the gates, and using these libraries. Are you guys looking at this at all?
So we know all the software that's available for simulating and implementing, well, I guess sending to the relevant libraries the quantum side of things. That exists. The software that's kind of missing is the part above that. So that part we presume that we already have. We know all the APIs, we know all the frameworks, we know that we have access to different kind of architectures, each with their own specifics on the physical side of things. They're all unique, they all have requirements. That we don't worry about. We don't want to rebuild that. That's not yet that's not necessarily our goal, even though at some point we may have to do, actually we will probably have to do fabrication, in which case we'll either need to adapt what exists or build something similar, but that's for later. Right now we have a big gap in the middle. Above that and below the protocol design level that people in crypto care about, or people in classical cryptography would care about, there's a big open space which is typically gapped, right now is actually almost entirely gapped by knowledge of people in quantum cryptography. And there are few quantum cryptographers. They're hard to train. They require years of expertise. Quantum cryptography is a very hard field. And so we try to make it possible for this to be faster, significantly faster. Because right now you have to do one protocol by hand with the intuition of the person doing it. We don't want that. That gets you maybe 3-party protocols with a flat causal structure. That's the best. 4 parties with a very regular structure, maybe. We want to have protocols involving complex communication, many parties with heterogeneous roles. Those are impossible today. It's just the polytopes involved are too big for practitioners to work by hand in reasonable times. So that's the idea.
Perfect, thank you.